Okay, guys. Hey, back here with Mr. Miller on lesson 16.5. If you're in the honors class, this would be lesson 17.5. Kind of a difficult section to take a look at. Our focus is on probability models, and I think this could be a little bit confusing compared to some of the other pieces that we've had in this particular chapter. So we'll start off with 16.5 key concept. And when we pull this key concept up here, I want you to note that a model has to consist of really three things. It has to consist of an action, it has to consist of all the sample spaces listed, and it has to consist of the probabilities themselves. You also have to note that each outcome in the sample space is in exactly only one event, and that the sum of the probabilities have to be one. As you can see here in this particular spinner situation, we have 5 different sectors, and in these 5 sectors, you can see that red is 3 times, so 3 out of 5 you could spin red theoretically, and that the probability of spinning a blue would be 2 out of 5. Again, please note all of those pieces the same exact size. So if I take 3/5 plus 2/5, I get 5/5, which obviously equals 1 in regards to that last piece where it says the sum of all probabilities must be equal to 1. Moving on then to part 1.
Wow. What's the probability of that? Oh, come on now. This is getting ridiculous.
All right, so you take a look at this particular situation. They're going to be talking about the action, which they said would be the first part, is to choose a card. Sample spaces, they've listed all 6 cards that you could possibly choose. And what you have to figure out is it list 1, list 2, or list 3 that does not complete the probability model for this particular situation. One of the key things I would be looking for is, does it add up to 1? You can see list 1 quickly is 1/3 plus 2/3. List 2, a little bit tougher to take a look at, but that should work as well. Let's go ahead and take a look at list 1. I think that's the easiest way to do it. So probability of fewer than 3 shapes. So this one has fewer than 3, this one has fewer than 3, and that would be it. At least 3 shapes would be these 4 right here. So in essence, what you have here is you have a probability of fewer than 3 shapes would be 2 out of the 6, which then in turn simplifies to 1/3, and 4 out of 6, which then in turn simplifies to 2/3. So this one should fulfill the idea of the probability model. Let's take a look at list 2. If I take a look at list 2, I'll erase these from up top, and we will now take a look at the fish, probability of fish. Once again, reminder, I have 6 cards here, so technically each of them would start with a denominator of 6. And so you can see probability of fish. I have a fish in this card, I have fish in this card, so that's going to be 2 out of 6, which simplifies to 1/3. Probability apple, apple would be 1 of them, 2 of them, actually 3 of them. So in this particular case, 3 out of 6 would simplify to 1/2. And then obviously our last one would be the leaf, okay? And in that particular situation, the leaf would pop up 1 out of 6 times, which you don't have to simplify that. But if you take a look at it, it's easier when you keep them in their common denominator. 2/6 plus 3/6 plus 1/6 equals 6/6, and obviously 6/6 equals 1. So we're good to go there. Last one, this must be the answer to the problem then, because obviously the other 2 fulfill the probability model. So if I take a look at the last one, you can see here the probability of an even number of apples. Even number of apples is going to be 1 out of 3. And you can see this is because I have 1 of them, 2 of them that have an even number of apples. That's 2 out of 6. Odd number of apples would be this cat right here. So there's my 1 out of 6. And in essence, what we could say is, hey, the 3 that I have not mentioned that have the X's on them right now were not even part of the mix. And so therefore, list number 3 is the one that doesn't fulfill the probability model. Moving on to part 2, or screen 2, slide 2. Erase all this quick. And in this particular situation, we have a robotics team. And in the robotics team, you're going to choose one member at random to run the robot competition. That's your action. They show you a list of all the sample spaces right here with the team. And then over here, list 1, list 2. They want to know what would you add to this in order to make it work. So in the case of list 2, you're either going to have boys or girls, obviously. And so as you take a look at it, list 2 must be probability of girl, and probability of girl has to be 2 out of 5. And I know that because 3/5 plus 2/5 has to equal 5/5, and if it equals 5/5, then that has to be equal to 1. So again, in this particular situation with 10 names on here, there better be what? 4 girls? 1, 2, 3, and 4. I move on to list number 2. List number 2, go back to my red here a little bit. I'm going to get rid of these check marks. Probability of people younger than 12. Younger than 12. So here's somebody who's younger than 12, younger than 12, younger than 12. So 3 out of the 10 represent younger than 12. People that are the probability of age 12. So here's a person age 12, here's a person age 12, and here's a person age 12, another 3 out of 10. So what we should be adding is probability older than 12 or greater than 12. And so in this particular situation, if I go older than 12, I do in fact have 1, 2, 3, 4 people who are older than 12. That would be 4 out of 10. Or if I simplify that, 2 out of 5. Okay? Once again, if you took 3/10 plus 3/10 plus 4/10, you're going to get 10 over 10, which equals my 1. Questions on that? About halfway home here. Moving on to my next slide. Explain why this list of probabilities does not complete a probability model for the spinner. So if you take a look at this, probability action would be spinning the spinner. Sample space, each of the 8 sectors is 1 outcome. So the probability of red, you can see, is 3 out of 8. Probability of yellow, obviously, is 1 out of 8. So our problem here lies in the fact that the probability of an odd and the probability of red, this cat right here is in 2 of these different sectors, and so is this dude right here. So obviously that's what negates this, is you have some sectors that are in it more than one particular piece. Questions there? Again, they're going to verify that in the probability model. Each outcome must only be in one event, and the number 1 is in the event red and in the event odd. Moving on to part 2 here. Part 2, and on part 2, again, that part 1 shouldn't have been too difficult. Part 2, on the other hand, again, this is going to get a little bit more abstract, I guess I would say. A probability model is based on using the theoretical probability of equally likely outcomes is known as the uniform probability model. You have to basically ask yourself, can I use theoretical probability here, or do I need to collect some data to use a relative frequency? So again, this is basically you telling yourself what's the difference between theoretical probability and experimental probability.
Which way?
You know the rules.
Really? Right.
Right, it is then.
I don't know how we are ever going to get to the park at this rate.
All right, so situation A. Okay, let me go to situation B first. You're playing a game. 2 friends are on a walk. At each intersection, they simply choose at random from 3 slips of paper. You can see the 3 slips of paper are turn left, go straight, or turn right. What's the probability that they will do that? So this is going to be an example of a theoretical probability because they're all equally likely to happen. Okay, equally likely to happen. That's theoretical. This one, on the other hand, wants to know the probability of a car waiting at the stop sign will turn left, go straight, or turn right. This one you'd have to run an experiment on. Take, for example, down here at the corner of Blue Lick and what is it, Slabtown, I guess it would be. You have that intersection right there. You know, if a car comes to a stop sign there, you have a better chance of going to the right, and in this particular case, I'd say towards Interstate 75, going to the left, which is back towards the city of Lima, or to go straight, which in this case would be to go away from Bath schools. All right, they're not equally likely going to happen. So we'd have to run an experiment in order to run that particular situation. Next slide. In this particular scenario, we'd have to take a look at situation A versus situation B. Now, situation B can be kind of confusing because you see we have 2 red faces versus 4 yellow faces. But what you have to kind of take a peek at is all 6 of those faces on this particular cube have the same chance of basically being rolled upon, all right? So what's the probability that the cube will land on yellow facing up? This would be 4 out of 6 situation, and therefore you could use a uniform probability model because it's 4 out of 6 versus 2 out of 6, okay? Your situation A, you drop a thumbtack from a height of 1 foot. What's the probability that the thumbtack will be land point up? Again, I don't think you can't sit here and tell me that the chances of landing on that head or landing on its side are going to be equally likely going to happen. So therefore, we would think that situation B, you could use a uniform probability model on. Yep, situation B only. And again, so I think that's a little confusing. I think you guys are going to find that a little bit confusing. Moving on to part 3 then. Got to get this in under 4 minutes. We're actually going to go straight to the source, and we're going to go to this one because I think you guys would connect with this one a little bit better. The data in the table from the survey of high school students with after-school jobs. We want you to write the list of probabilities for the probability model that gives the probability that a student who is chosen at random from this group of high school students has each type of job. Sorry about that, had to run to get a calculator based upon these numbers. So if we take a look at this, we could sit here and say, hey, if I took 67 plus 8 plus 120 plus 55, I'm at 250. So in this particular situation, we're at 67 over 250 for the store cashier, 8 over 250 for the paper route kid, 120 over 250 for the restaurant or the babysitter, and then 55 out of 250 for the restaurant worker. So if we would basically calculate those out, 67 divided by 250, I'm going to change those to it's approximately 27%. 8 out of 250, if I divide that out, is approximately what? 3.2% or 3%. 120 over 250 is about 48%. That's actually exactly 48%. Then 55 over 250 is exactly 22%. So when I add those together, I get my 100% in that particular situation. Okay. So the question asked me, write the list of probabilities for the probability model. And so I'm going to hit correct answer here, and it should verify, hopefully, what we said here. If I move this stuff out of the way, the cashier was 27%, I said. The paper route kid was 3%, I said. 48% for the babysitter, and then 22% for the restaurant worker. All right? That should conclude 16.5. Again, good luck. If you have any questions, please shoot me an email. You've been doing a great job of keeping in contact with me. We're going to work on maybe doing some Zoom stuff. I'm going to guinea pig that tonight, so we'll see how that plays out. All right? You guys stay safe. Bye.